So when we're looking at factorials, what we're looking at are products of descending integers. Roughly what a factorial does is it takes some value n and multiplies it by all of the natural numbers below it. So something like 8 factorial has form 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and something more generally like n factorial has form n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times all the way down to 3, 2, and 1. Where if you want to understand what a factorial represents, in my opinion, the easiest way to think about that comes from a nice counting definition that you've probably seen if you've taken a statistics class before, where if you have some arrangement of n things, like say if you're watching a race,
they're off.
And in that race you want to be able to determine who comes in first, second, third, and so on. That is, you want to select all of the members of the race and organize them in such a way that you're going to use all. That is, you're going to select all of them where there are no repeats. Well, you'd have, if it's 8 options for the first, and 8 for the second, and 7 for the 8 options for the first, 7 for the second, 6 for the third, and so on, because something can't both come in first and second at the same time.
My wife knows everything in front. To the outside, the wife doesn't know. My wife knows everything. The wife doesn't know. My wife knows everything. More than the wife doesn't know. Whew.
And why the book doesn't include that combinatorial idea, I'm not entirely sure, but it is what it is. Anyway, to bring it back to recursion, when thinking about these values with factorials, it is very easy to think about a factorial recursively, because if you want to get the nth term in a sequence that's just factorials, well, you take the one before it and you multiply it by n. And these things give rise to some very nice little patterns that you'll see more of if you take a stats class, and if you want more information about this stuff, you want more of an understanding of these that isn't just sort of talked straight through here, let me know, because I do have a lot of notes and a few videos on these, because, well, I've taught them quite a few times. But anyway, for now, we're just going to take a quick example looking at these in the context of sequences. So for this example, we want to write the first 4 terms of the sequence whose nth term has the formula an equals 30 over n minus 1 factorial. So it's the same idea we've been using all the way through here. For a1, we're just going to take that value, 30, and divide by 1 minus 1 factorial, which is going to be 30 over 0 factorial. And I will say that 0 factorial is a very special value. For the sake of convenience, we define 0 factorial to be 1, but there's also a sort of combinatorial argument, a counting argument for why 0 factorial equals 1, where it makes sense if you think about that as saying, how many ways can we arrange nothing? Trivially, we can only arrange nothing in the way it is, as nothing. So there's one free way to arrange nothing, which means that 30 over 0 factorial is just 30 over 1, or 30. And it's also going to be equal to 1 because it helps with some very important patterns that we'll see more of later. Anyway, we have that for our first term. For our second, for A2, shouldn't stand in the way of my typing, we're going to have 30 over 2 minus 1 factorial, but that's just going to be 30 over 1 factorial. And the only natural number less than 1 is 1. So it's just 30 over 1 again. Still 30. It's not very interesting. But this won't just be a sequence of 30s. We'll get something soon. At A3, we'll take 30 over 3 minus 1 factorial, which is going to be 30 over 2 factorial. And thank you, we get a number that's not 30, because 2 factorial is, well, it's 2. It's not that exciting, but it's more than 1. It's good enough for now. Anyway, we're taking 30 over 2, which would just be 15. And then finally, for A4, we would have 30 over 4 minus 1 factorial, which is 30 over 3 factorial, where 3 factorial is 3 times 2 times 1, or 6. So we would get 30 over 6, or 5. And if we wanted a recursive definition for this, like I said, dealing with recursion in the case of factorials, it's not that complicated. Here, we could recursively define this as a1 equals 30, and an equals an minus 1 divided by n minus 1, where it is actually very important in this case that we have that recursive definition with n minus 1 starting at 2, because if we start at 1, we'd be dividing by 0, and even for discrete things, we don't like dividing by zeros. Don't do that. Don't do that. 0 factorial is fine, but we need that exclamation point. 0 needs to be happy to be here, I suppose, if it wants us to do anything. But anyway, from here, it is important to note that we're dealing with factorials. The value n times m factorial is generally much smaller than the quantity n times m factorial. So for example, if you take something like 3 times 2 factorial, that would be 3 times 2, or 6. Whereas if you took 3 times 2, you would get 6. Take the factorial of that, and it's 6 times 5 times 4 times 3 times 2 times 1, which is 120, which is, hopefully you can tell, much bigger than 6. The only time, in fact, where this doesn't hold, where these are equal, that I know of offhand, is when one of n or m is equal to 1, and it's not much of a multiplication. It can happen, and there are some other special cases where it does, but very, very rarely does that occur. Usually, this is the sort of relationship you have, so be careful when you're multiplying with factorials that we treat this with some special care. Anyway, from this, we're going to shift gears again, to think of a new phrase other than shifting gears, but we're going to talk, for our last thing, about how we can look at adding up the terms of a sequence with a bit called summation notation.